In this video, I'm going to explain the boosting algorithm, and then we're going to implement it in Python. And specifically, we're going to implement the adaptive boost algorithm. One simplification I've made is that we're going to do binary classifications. So for each of our input vectors, or each of our input records, we're going to output a plus or minus 1. And so obviously this requires some basic AI knowledge, but if you have that, let's get started. Oddly enough, the fundamental idea behind boosting can be found in the first Planet of the Apes movie. Just replace ape with classifier, and you've got the boosting algorithm. So classifiers by themselves might be weak, but we can combine a bunch of weak classifiers to create a strong classifier. And that's the fundamental idea behind boosting, is combining a bunch of weak classifiers to create a stronger classifier. So a weak classifier might classify things correctly. In our case, we're doing binary classification, plus or minus 1. It might classify things correctly 60% of the time. A strong classifier classifies things correctly 90% of the time, or 95% of the time. So what we're saying is we can take a bunch of these weak classifiers that aren't very good at classifying things, and combine them to create a classifier that's very good at classifying things. So here I've drawn out a two-dimensional representation of the type of problem that we're trying to solve. So let's say the x-axis is weight and the y-axis is height, and we're trying to predict whether someone's an NFL player or not. So this person is a small NFL player, this is a big NFL player, and these are two medium-sized people that don't play in the NFL. And so we're given a big table of people's heights and weights and whether they're NFL players or not, and our task is to build a classifier that can take in a new weight and height and predict whether they're going to be in the NFL. And so the concept of boosting requires a bag of classifiers. And so what you need is a whole bunch of classifiers, and they don't have to be good classifiers, that divide up your data in different ways. And this is one way to do it. You can just do it by dividing it up in each dimension. Here we have 2 dimensions, so I've got vertical lines and horizontal lines, but if you had higher dimensions, you would just draw lines between the data in each dimension. And so let me explain this line here. So each of these lines actually corresponds to 2 different classifiers, because I could say, okay, to the left of this line, I'm going to classify anything to the left of this line as positive. Or I could say, I'm going to classify anything to the left of this line as negative. And those are both valid classifiers. They might be terrible. One of them is going to be terrible. They might both be terrible. One of them might be wrong 60% of the time. The other one's wrong 40% of the time. But those are both pretty bad. But both of them, even the one that's wrong most of the time, you might use in your algorithm later. So you just want to build up this kind of bag of classifiers by dividing your data like this. So that's kind of the first step. So now I'm going to give you some intuition for the boosting algorithm. It's like choosing a team for trivia night. So let's say you have 5 friends. These are your 5 smartest friends, the only friends that you're considering to be on your trivia team. And you're wanting to build a 3-person trivia team from these 5 friends. And although each of these friends is very smart and they get most of the questions right, they do have areas of weakness. So Bob misses a lot of the history questions, Claire misses a lot of the pop culture questions, and so on and so on. If you draw this out, this is kind of a pictorial representation of this table, where Bob and Ernest both miss a bunch of the history questions. So they both miss a lot of the same history questions, and Bob might get a history question right when Ernest misses it, and vice versa, but by and large, they both miss a lot of the history questions. Dylan misses the geography questions, but no one else is bad at geography. So when Dylan gets it wrong, everyone else gets it right. And then Claire and Felicia is interesting because Claire's bad at pop culture. Felicia's also bad at pop culture, but she's also bad at biology. So every one of the pop culture questions that Claire gets wrong, Felicia seems to get wrong, but Felicia also misses the biology questions. So this is a pictorial representation of this table. And when you look at it in this way, it's kind of clear how you should pick your trivia team. You definitely want Dylan on it. You'll pick Claire. You'll always pick Claire over Felicia. Just the fact that Claire is there means that you're never going to pick Felicia, because Claire's just Felicia but better. And then you're either going to pick Bob or Ernest. So it kind of doesn't matter in this case which. They're both kind of bad at history. You just don't want both of them, because that just gives you two people that are bad at the same thing. And the point of this is that you want a team where you want to pick your smartest friend. Say your smartest friend is Bob first, but he's bad at history. So the next person you're going to pick is going to be someone that's not bad at history. So once you've picked Bob, you're definitely not going to pick Ernest after that. You're going to pick someone who's not bad at history. You're obviously not going to pick Felicia, because as we've discussed, Claire is better. So maybe you pick Claire next. Well, now you want someone who's not weak in the same areas as Claire and Bob. And the only person left like that is Dylan. So your team is composed of Bob, who's weak at history, Claire, who's weak at pop culture. You want someone who's not weak in either of those areas, which is Dylan. So you want someone from each one of the areas. This is essentially the boosting algorithm. That's what you do, is you pick your best classifier first, and then your next classifier is going to be a classifier that is better at classifying the ones that the previous classifier got wrong. So this is just writing out the algorithm we just went over. You start with your smartest friend who gets the least questions wrong, like Bob. Then we choose a friend who is good at the areas where Bob is weak, like Claire. And then we choose a friend who's good at the areas where Bob and Claire are weak, or Bob or Claire are weak. So Bob's bad at history, Claire is bad at pop culture. So you want someone who's not bad at history or pop culture. And so on if you were building a team with more than 3 people in it. But instead of starting with a group of friends, boosting starts with a bag of classifiers. That bag of classifiers that I described earlier, where you're just kind of randomly dividing your data, and they could be terrible classifiers, but you just want a whole bunch of different classifiers to choose from. And then, so the first step in this is easy. Choosing the best classifier, you just run all of your bag of classifiers over all your data and find the one with the highest accuracy. But how do you choose a classifier? How do you choose the next classifier? The one that's specifically better at the ones that the first classifier missed. So here's where the math comes in. So for each of the training points or records or rows, that would be those 2-dimensional vectors that I graphed earlier, the heights and weights. For each of those heights and weights we're given in our training data, we're going to assign it a corresponding weight WI. So for each of the training records XI, we're going to assign it a corresponding weight WI. And then we're going to define an error score for every classifier as the ones that classifier got wrong, that it's just going to sum up the weights corresponding to the data points that it classified wrong. So for each classifier, they're going to have a different error score depending on which data points they got wrong and what the weights corresponding to those data points are. Now, initially, we're going to weight all the points evenly. So if we have 4 points, we're going to weight it 1 over n, where n is the number of training points. So we have 4 points. Each of the weights is going to be 1/4. And so what this error score does is just it adds 1/4 for each of the ones that you got wrong. So on each iteration, what we're going to do is we're going to choose the classifier with the smallest error score. The first one's easy. It's weighting all of the points evenly, and so it's just going to end up choosing the classifier that classifies the least points wrong. And that's the easy one. But so the trick comes how you choose the next classifier that is better at getting the ones that you just got wrong right. The trick to that is that we're going to scale the weights. So we're going to weight the ones that we just got wrong more. We're going to weight the ones that we just got right less. And then we're going to recalculate each of the error scores for each of the classifiers. So even though each classifier has certain points that it got wrong, and that will never change. If one classifier classifies points 2 and 6 wrong, that will never change as we go through this algorithm, but the weights corresponding to each of those points might change. So the error score for each of the classifiers needs to be recalculated on each iteration. And what's going to happen is we're going to kind of upvote the ones that we got wrong, so that when we miss those, they contribute to the error more. And so when we choose the one with the minimal error, it's going to tend to be better at the ones that we just got wrong, because we scaled those weights up. And so minimizing this is going to choose the classifiers that don't miss those. So that's the trick to the algorithm right there, is this scaling of the weights. We're just exaggerating the contribution of the ones that we just got wrong. We're exaggerating their contribution to the error, so that when we choose the minimal error, we're choosing a classifier that doesn't miss them as much. And we'll just keep doing that. So every iteration we're choosing a new classifier to kind of add to our combination classifier. So these are all pretty bad classifiers, but we're slowly building up a classifier that's a combination of all these classifiers that's going to be very good. And so each iteration we choose one more classifier to add to the combo classifier, and we scale the weights. And that's all this algorithm is. So this is a very scary slide. I won't spend a whole lot of time on it. If you want more of this super math stuff, I'll say watch the MIT lecture by Patrick Winston that I linked below. And there is also a TA lecture that goes along with that helps fill in some of the gaps from Patrick Winston's lecture. Those are both very good lectures. I highly encourage you to check them out. But essentially, if we label each of the weak classifiers that we're dealing with as H, then H of xi, where xi is one of the training points, that just gives the classification that weak classifier outputs for that point. So that weak classifier might think that, the point that this training point maps to +1. The y of x here is the true classification of that training point. So if I multiply h of x times y of x, that's going to be +1 if h of x is the same as y of x, if the weak classifier got it right, and it'll be -1 if the weak classifier got it wrong. And so what this equation is how to scale the weights. So I know I said on the last slide that, the weights scale this way. This is totally true if you scale the weights like this, and you define the alpha here to be of this form. And that might seem kind of surprising, but if you look at this, the alpha has a natural log here, and so it's e to the natural log of something. Natural log and the exponential are inverses of one another, so this expression actually simplifies a bit, and you can show, and he does that in the lecture, that this amounts to just saying that the sums of the weights over the ones you just got wrong and the ones you just got right are both equal to 1/2 over all iterations. So this is a way easier way to scale the weights than computing all these exponentials. So this is the way you do it in the code, and you never even mess with these exponentials in the code. But this is actually a result of assuming that the weights are scaled, are transformed according to this equation with these alphas. So if you want more on that, and also choosing these forms for the alphas and the weights also bounds the error so the solution converges better. So if you want more on that, check out the lectures. So we've discussed a lot about how to choose the weak classifiers to add into our combination classifier, but we actually haven't discussed how to combine them. And this is it. It's just a linear combination of the weak classifiers that we choose at each round. So this is the weak classifier that we chose on round 1. This is the weak classifier that we chose on round 2, and etc. And you can go for as many iterations as you want. Where you should stop is a bit of a complicated question, so I'm not going to go into that, but you can just kind of experiment for yourself where you should stop. There are some data sets where you can keep going until you get 100% accuracy, but that might be overfitting, etc. But you can see that these weak classifiers, for each iteration you choose one, and then you also multiply it by some coefficient in this linear combination that you're creating. And that coefficient is the alphas that I gave on the last slide. It's 1/2 the natural log of 1 minus the error score from that classifier in that round. So whatever its error score was, that was the minimal error score for that round, is the epsilon that occurs right here in this alpha. And the way I've arranged this is each of these weak classifiers is going to output a positive or negative 1. Well, this big H, the way I've written it, is not going to output just positive or negative 1. It's going to be some, combination of positive and negative 1s times some real numbers here, these alphas. So it's going to be just some random real number. So you can map that. You can just say, okay, well, all these values that are greater than 0 or greater than or equal to 0 are positive 1, and then all of them that are less than 0 are negative 1. And so that is our strong classifier that we've created from a combination of the weak classifiers using these coefficients at each round. And again, you can just have as many terms in here as you want. You can iterate as long as you want, but you probably will be overfitting at some point. Okay, I wanted to briefly take you through the code, and I'm going to start by running it and show you what it outputs. So it randomly generates 100 points in two-dimensional space, and it randomly labels each of the points as either plus or negative 1, indicated by the two different colors there. And the goal of the algorithm is to take a bunch of weak classifiers and build up a strong classifier from those weak classifiers to correctly classify each of these training points. And my bag of weak classifiers is exactly what I showed before in the previous slides. I draw a vertical line in between each of the different x coordinates here, and a horizontal line in between each of the different y coordinates. And there's also two extra classifiers that I didn't mention earlier that are mirror images of one another. I classify all of the points as true or +1, and all of the points as -1. So that could be thought of as either a vertical line like way out here, or a horizontal line like way down here or up here or something. But it's not between the points, it's like to the left or right or bottom or top of all the points. And you only need one of those, and then you need to take the mirror image of it. Just wanted to mention that. The other side of this graph is the accuracy as we're increasing the number of iterations. And obviously, the more iterations you do, the better this thing's going to get. And each iteration adds one of the weak classifiers to the combination. So an important point that I want to make here that I didn't mention earlier is you can reuse weak classifiers from your bag of classifiers. So say I had a classifier right here that classifies everything to the left as true and everything to the right as false. I could reuse that 4 or 5 times in my linear combination. I could use it at iteration 50, and then maybe it's got the lowest error score again at iteration 150, and then again it's got the lowest error score. There's no rule that says that you can't reuse a classifier. The TA mentions that you can't reuse it twice in a row because that ends up getting you into an infinite loop, and I'll let you think about that on your own, but essentially the reason is because the weights do not scale the second time. You've already scaled them such that the error score is going to be 1/2, and if you're choosing the thing with the lowest error score and it's already 1/2, then no scaling is going to be done, and so you're always going to end up choosing that same classifier, and nothing's ever going to happen. But I haven't run into that situation. I believe to run into that situation, you'd need all of your classifiers to have exactly an error score of 1/2, which seems unlikely to me, but maybe with really small data sets or something, you might run into it. Anyway, so this is what it outputs here. Now let me take you through some of the code. So all this up here is just kind of defining different classes and functions, and the execution of the code starts here. So time to run the boosting algorithm. So this just reads in your input data. This is these features are kind of the column definitions. So whether it's binary data or numerical data, this is the actual training data itself, and these are the labels for the training data. So if I have 100 points here, then I'm going to have 100 labels for it. This function generates the classifiers. Let me just go over kind of broad strokes here, and then I'll pop into a couple of these. So this generates all the weak classifiers, the bag of classifiers, those horizontal and vertical lines, and then it uses the bag of classifiers, and for each classifier, it classifies all of the training data. All of the training points get classified by each classifier, and each classifier will store which points it got wrong. So I also pass in the labels there so it can tell, did I classify this right or wrong? And so I store on each classifier which points it got wrong. That will never change through the entire algorithm. The weights of the points that it got wrong changes, but the points that it got wrong do not change. So I just do that once at the beginning, print out all the classifiers, then I eliminate the dominated classifiers. So if you remember in previous slides, I talked about Claire and Felicia and how you would never choose Felicia because you've got Claire, and Claire is always better in every circumstance. This is what eliminates Felicia. Bye, Felicia. This is what does that. So, and then I print out my classifiers all over again because I've eliminated some of them. I've said bye to Felicia. And then I go through my algorithm here. So what I do here, so this is maybe a little bit confusing, and I did just change this just before this video, but essentially what this does is it builds up the strong classifier, and at every iteration, it yields back the strong classifier at that point. Originally, the first time I wrote this, I just said, hey, build me a classifier and, go for 10 iterations or whatever. And so then when I wanted to see, okay, well, how does the accuracy increase as the number of iterations increases, I just put that in a loop. But that created nested loops where I was doing a lot of the same computations. I'd build up a strong classifier, with 150 iterations, and then I'd start all over to build up a strong classifier with 151 iterations. So that's why I changed this to yield back the progressively better and better strong classifier at each iteration. And so I go through this loop, and for each of the strong classifiers that it yields back, I calculate the accuracy and add it to the plot. And so that's all that does. So let me pop into not only this function again, but I want to start with generating the classifiers. So what this does is it says, okay, it takes those column definitions that I mentioned earlier, and it says if it's a binary classifier, then just make these two classifiers where it says, okay, if the value in that column is true, then output, true or +1. And then the mirror classifier to that would be if the value in that particular column is not true, or in that particular dimension, you might think of this in a visual way. This is dealing with a particular dimension. So this is looping through all of the dimensions in your training data, and it's saying if the value in that dimension is true, then output true. And then the mirror classifier is if the value in that dimension is not true, output true. Okay. And then the other possibility, the only other possibility in this case, and other than binary, is a numerical feature where it's a number like 2 or 2.3 or 500 or whatever. And for that, I need to actually find, I call this other function that basically sorts all of the values in that dimension and then just kind of draws a line midway between each of them. That's all this is doing. And then it makes the mirror classifiers by saying, okay, well, if it's, whatever my cutoff is, if the value in that column is greater than that cutoff, then output true. And then the mirror classifier is if the value in that column is less than or equal to that cutoff, output true. Okay, and it, gets all those. And then this is the other classifier I mentioned where it just says, I don't care what's in any of the columns, just this a valid classifier is saying that all of the points are classified as +1. And another valid classifier, the mirror image, is all of the points are classified as -1. So that's all this does. It grabs it goes through each of the dimensions in your data. It finds all the classifiers for any of the binary dimensions, and it does a more complicated, more computationally expensive computation for any numerical columns that you have, because it has to sort all of the values in that column and then draw a vertical, or if you want to consider it, horizontal line between each of the values. Okay, and it returns all those classifiers, and that's your bag of classifiers. So that's kind of that function explained. And then I'm not going to go through eliminating the dominated classifiers, but essentially what I do in there, it follows very closely what happens in the TA lecture. So if you want to really understand like what we're doing there, you can either read my code. It should be fairly easy. It's not a hard function, but you can either do that or watch the TA lecture. Okay, and then the other function that I wanted to go over is generate strong classifier iterator. So, I added iterator on there because it yields back values, and it'll yield back, multiple strong classifiers as it's building it up. But okay, so here, this is the entire algorithm right here. So for each iteration, so first I initialize the weights, and I initialize my strong classifier. And for each iteration, all I'm going to do is find the classifier out of my bag of classifiers with the minimum error score, and I'm going to use that error score to calculate the alpha, because the alpha is 1/2 the natural log of 1 minus the error score divided by the error score. So alpha is a function of the error score. So here I'm calculating the alpha, and then I just add it to the strong classifier. So that's going to become part of that linear combination. It's going to be that weak classifier times the coefficient alpha, and that's going to be added to the linear combination. And then I'm just going to rescale the weights. And rescaling the weights is really simple. You just take the weights and the points that the training points that the last classifier got wrong, and you say, okay, well, I'm going to sum up the weights of all the ones that I got wrong, and I'm going to sum up the weights of all the ones that I got right. And all I'm going to do is every weight is going to be divided by the sum of the wrong. Every weight corresponding to one of the points that I got wrong will be divided by the sum of the wrongs and multiplied by 0.5, and that will ensure that the sum of the wrongs after this transformation is 1/2, and similarly, it will ensure that the sum of the rights after this transformation is 1/2, and that is the rescaling that we do for each iteration. And at that point, you're done. I mean, that's the entire algorithm right there, and then it yields back that strong classifier, and you can use it to classify your training data. And that's it. That's a simple implementation of boosting. So the code I just went over is linked in a GitHub repo in the description below. Feel free to grab it and play with it. Just be forewarned, it's not production ready. I haven't optimized it. There's tons of optimizations that you can do to that code, so feel free to play around with it yourself. But thanks for watching.